What if I told you that the light streaming through your window right now began its journey over 100,000 years ago? That right now, the sun is releasing energy equivalent to 6 trillion nuclear bombs every single second? And that this massive ball of plasma is so large that you could fit 1.3 million Earths inside it? The sun isn't just a bright light in our sky, it's the most powerful object in our solar system, a nuclear furnace that's been burning for 4.6 billion years. Every breath you take, every plant that grows, every weather pattern on Earth, it all depends on this incredible star that's 93 million miles away. Today, we're going on a journey inside the sun itself. We'll explore its 6 distinct layers, uncover the mysteries of nuclear fusion, and discover why the sun actually gets hotter as you move away from its surface. By the end of this video, you'll understand how this cosmic powerhouse works and why it's literally the reason life exists on Earth. So buckle up. We're about to dive into the most extreme environment in our solar system. Our story begins 4.6 billion years ago in a region of space filled with nothing but gas and dust. This wasn't the organized solar system we know today. It was a chaotic cloud of material called a solar nebula, drifting through the darkness of space. But then something happened. Maybe a nearby star exploded, sending shockwaves through the cloud. Maybe it was just the natural pull of gravity. Whatever the trigger, this massive cloud began to collapse in on itself. As gravity pulled the material together, something incredible occurred. The center of the cloud became denser and denser, hotter and hotter. Imagine all that material, enough to create our entire solar system, being compressed into an increasingly smaller space. The pressure became unimaginable. When the temperature at the core reached 15 million degrees Celsius, nuclear fusion ignited. Hydrogen atoms began smashing together with such force that they fused into helium, releasing enormous amounts of energy. At that moment, our sun was born. But here's what's truly mind-blowing. The sun captured 99.86% of all the material in that original cloud. Everything else, all the planets, moons, asteroids, and comets in our solar system, formed from the leftover 0.14%. The sun is so massive that its gravity controls everything within billions of miles. This wasn't just the birth of a star, it was the creation of the gravitational anchor that would hold our entire solar system together. But what exactly is happening inside this cosmic furnace that makes it so powerful? Welcome to the most extreme place in our solar system, the sun's core. If you could somehow journey to the center of the sun, you'd find yourself in conditions that are almost impossible to imagine. The temperature here reaches 15 million degrees Celsius. That's 2,700 times hotter than the hottest lava on Earth. The pressure is 250 billion times greater than the atmospheric pressure at sea level. It's so dense that a single teaspoon of core material would weigh about 150 grams, roughly the weight of a baseball. In these extreme conditions, something extraordinary happens every second. Hydrogen nuclei, the simplest atoms in the universe, are moving so fast and colliding with such force that they overcome their natural repulsion and fuse together to form helium. This process, called nuclear fusion, converts a tiny amount of matter into pure energy. And when I say tiny, I mean tiny. Only about 0.7% of the hydrogen's mass becomes energy. But because of Einstein's famous equation, E equals mc squared, even this small amount of matter creates an enormous amount of energy. How enormous? Every second, the sun converts 600 million tons of hydrogen into helium. And in the process, 4 million tons of matter completely disappears, transformed into pure energy. That's equivalent to exploding 6 trillion nuclear bombs every single second. This energy is what powers the sun, what lights up our sky, and what makes life on Earth possible. But here's the incredible part. This energy doesn't just instantly shoot out into space. It faces an epic journey that takes longer than human civilization has existed. The energy created in the sun's core begins its journey as high-energy photons, particles of light. But these photons face an almost impossible challenge, escaping through the radiative zone, a layer that extends from the core to about 70% of the sun's radius. Imagine trying to walk through the world's most crowded room, where every step forward requires you to stop, turn around, and change direction. That's essentially what happens to photons in the radiative zone. This region is incredibly dense, packed with particles that constantly absorb and re-emit the photons. A single photon might travel just a few millimeters before being absorbed by an atom, which then re-emits it in a completely random direction. It's like a cosmic pinball machine where the photon bounces around randomly for thousands of years. Scientists estimate that it takes between 100,000 to 200,000 years for energy to travel from the sun's core to its surface. Think about that. The sunlight, hitting your face right now, began its journey when woolly mammoths roamed the earth. The energy that powered the dinosaurs is still making its way through the sun's interior. This incredibly slow journey is why the sun is so stable. Even if nuclear fusion in the core suddenly stopped today, the sun would continue shining for hundreds of thousands of years, powered by the energy still making its way outward. But eventually, after this epic journey through the radiative zone, the photons reach a very different kind of environment, a place where the sun's material is literally boiling. As we move outward from the radiative zone, we encounter the convection zone, a region where the sun's material is in constant violent motion. Here, the temperature has dropped enough that the material becomes opaque, and energy can no longer travel efficiently by radiation alone. Instead, the sun transports energy through convection, the same process that makes water boil in a pot. Hot plasma rises toward the surface, cools down, and then sinks back toward the interior, creating massive convection currents. These aren't small bubbles like you'd see in boiling water. We're talking about convection cells that can be larger than Earth itself, with plasma moving at speeds of several kilometers per second. From space, these convection cells create a granulated pattern on the sun's surface, like a cosmic honeycomb. Finally, we reach what we call the sun's surface, the photosphere. This is the layer that emits the light we see, and it has a temperature of about 5,500 degrees Celsius. While that's incredibly hot by Earth standards, it's actually much cooler than the sun's interior. The photosphere is where we observe many of the sun's most dramatic phenomena. Sunspots appear as dark patches. They're actually cooler regions caused by intense magnetic fields that inhibit convection. These magnetic fields can also create solar flares, explosive releases of energy that can send radiation streaming across the solar system. We also see solar prominences, massive arcs of plasma that can extend hundreds of thousands of kilometers into space, held in place by magnetic field lines. These features remind us that the sun isn't just a static ball of gas. It's a dynamic, ever-changing star with a complex magnetic personality. But here's where things get really mysterious. Logic tells us that as we move away from the sun's nuclear furnace, temperatures should continue to drop. But that's not what happens. Above the photosphere lies one of the sun's greatest mysteries, layers that actually get hotter as you move away from the sun's core. This defies everything we'd expect from a cooling star. First, we encounter the chromosphere, a thin layer that's normally invisible to the naked eye. During solar eclipses, when the bright photosphere is blocked, the chromosphere appears as a reddish glow around the sun's edge. Despite being further from the sun's nuclear core, the chromosphere reaches temperatures of up to 20,000 degrees Celsius, nearly 4 times hotter than the photosphere below it. But the real mystery lies even further out, in the corona, the sun's outermost atmosphere. The corona is a wispy, ethereal region that extends millions of kilometers into space. During a total solar eclipse, it appears as a beautiful, shimmering halo around the sun. Here's what's absolutely mind-blowing. The corona reaches temperatures of over 1 million degrees Celsius. That's nearly 200 times hotter than the photosphere and about 50 times hotter than the chromosphere. It's like discovering that the air above a campfire is hotter than the flames themselves. So what's heating these outer layers to such extreme temperatures? Until next time, remember that every sunrise is a reminder of the incredible nuclear furnace that makes life on Earth possible. Keep looking up and keep wondering about the amazing universe we call home.